Okay, we are going to finish up Chapter 2 today. This is a segment called Normal Probability Plots. And this is your last video before the test. So today's standards, what we are going to do is discuss more of the properties of the normal distribution and how it is that we can identify a normal distribution. So today, what we really want to cover is when can we call something normal, and we're going to figure out best ways that we can estimate it. So we're going to use normal probability plots, but before we get to a normal probability plot, what we have on our in our arsenal of tools to use, we have the empirical rule, and the empirical rule is also called the 68, 95, 99.7 rule. But that rule tells us that 68% of our data should fall within 1 standard deviation of the mean, 95% should fall within 2 standard deviations of the mean, and 99.7% should fall within 3 standard deviations of the mean. So if we have a data set and it follows those rules, we can believe that our data is normally distributed. There's a little bit more we can do to find out if it's normally distributed, and we can use something that's called a normal probability plot. Now, the normal probability plot is a little bit mathematics and a little bit voodoo, so we're just going to use it as a tool. It's kind of a guide. It's not exactly a precise science, but we're kind of reading a little bit of tea leaves in this. So we'll see how that we do this. First, about the normal probability plots. They're used to assess normality. So when you construct a normal probability plot, if the points form a relatively straight line, the data is considered normal. So that's what we're looking for, our data to form a straight line. Well, the x values of our data are the data themselves. The y values are the z-scores of the data values, which is a little bit of where the voodoo comes in. So, but that's how the normal plot is constructed. So we look for deviations in the pattern. If it doesn't form a straight line, we're curious as to what pieces don't follow the straight line, and if it doesn't form that straight line, the shape that it does form can tell us about the shape of the distribution and why it doesn't fit the normal probability approximation. So here are some examples of how it would not be normal. Now, this red line here, if our distribution followed the red line, it would be considered normal. However, we see that it kind of bends upwards. In that case, that distribution that made that bending upwards shape is skewed right. So if they appear to bend up, the left of the normal line has a long tail, then it has a long tail to the right, your distribution does. So if it bends up towards the left, it has a long tail to the right, which means our distribution is skewed right. If it bends down, so to the left, to the right of the line or below it, that distribution has a left skew. So just like the right. So these are different skews. And we can also tell about the tails. Here, we've kind of got an S shape. That S shape tells us that that distribution has short tails. So they're shorter than a normal distribution. So it has less variance and not as long. Okay. If it has kind of a cubic shape, that's a curve that starts below the normal line and bends to follow it. Okay. These are distributions that have a longer tails, therefore the variance is more than what a normal distribution covers. So these are the ways that it does not follow a normal plot, and we can't call it normal, and the reasons why and the shapes of the distributions that don't follow the normal distribution as it should. Okay, here are the lengths and feet of 44 great white sharks. And we're going to do part of this today, and we're going to finish this in class. I'm going to show you how to do a normal plot in your calculator. So if you want to be prepared in advance, you should program these lengths into one of your lists in your calculator so that we can use it in class for your normal plot. But we're going to have to program them into our list now in order to find some statistics about those lengths, because we're going to compute one variable statistics on them. Describe the distribution of these lengths. Well, what we can do is plot a histogram with our x values here in a stat plot. You can plot your histogram in your calculator, and we see that it is symmetric and somewhat uniform. Okay, let's compare the mean with the median. Okay, the mean is 15.59 and the median is 15.75, and we got that from one variable statistics on it in our calculator. Now I see that they're very similar, so close to symmetric, and now I'm going to see if it's approximately normal by doing two things. First, what I'm going to do is see whether or not it follows the 68, 95, 99.7 rule. I see within one standard deviation, because our standard deviation was given to us in our one variable statistics, and our mean was 15.59. Within one standard deviation, 68.2% of my data is there because 30 values fall between those two numbers in my data. Add another standard deviation and subtract another standard deviation, and I get a new range. So between 10.486 and 20.686, I find 42 out of the 44 shark lengths. And within 3 standard deviations, that means between 7.936 and 23.236, I find all 44 out of 44. So I see 68%, a little bit more than 68, a little bit more than 95, and a little bit more than 99.7, but it's really close. So is it normal? Well, tomorrow what we're going to do is use that list in your calculator to construct a normal probability plot, and we will judge from there whether or not we think it's normal. We can go off of the graph that I have for now. I'm seeing data that's pretty close to a straight line. I might have a couple of pieces here. So I want you to, in your best judgment, using this and the plot that we will do with our calculator tomorrow, we're going to write a summary of our assessment that combines our findings of, does it follow the 68, 95, 99.7 rule, and the normal plot, does it follow a straight line close enough for us to determine whether or not it's approximately normal. And that's it for today. We'll see you tomorrow.